Well, okay, boys and girls. It is 8:30. Time to start period 1. Everybody's doing well. We still got a lot of people missing. Oh, well, it's the first norm that you set up in meetings is, respect start times and respect the end times. So I'm just going to go ahead and get started. Nothing new really on business aspects that we didn't go over yesterday in class. I haven't had a chance to look at any of the responses for the feed the monkey thing. So hopefully that went well. I didn't have any trouble with that. And we'll just start in with do more relative motion stuff. We'll see how far we get today. Remember, this is going to be the last topic for the chapter 4, and chapter 2 and chapter 4 are kind of a unit. Normally what I would do in class at this point, once we get done with chapter 4, is we would schedule a big, huge, important test. And I'd give you, I would normally format it like the AP test. It'd be 3 free response questions, and be with a heck of a lot of points. Because now we're online and we're doing things differently, I'm kind of spreading the points around a little more evenly between the different things we're doing. So we will be doing a chapter 2, 4 assessment. I'm not even going to call it a test. I'm going to call it an assessment, because it's not going to be anywhere near as many points as a test would be. It's going to be the same number of points as like your labs. So so the feed the monkey thing is going to be is going to be just the same number of points as the chapter 2, 4 assessment. So I haven't got a date for you yet. In fact, I haven't even finished putting the assessment together yet. So I got to do that first. And so this probably won't be till, because we're on this block thing, probably won't be till next week sometime. But I'll try and get it together and a date for you by Thursday when we meet again. And it'll cover just chapters 2 and 4, not 3 per se. I mean, in chapter 4, we do stuff with vectors, right? We do vector mathematics, but I'm not going to give you problems directly out of chapter 3 that are just vector mathematics problems. Does that make sense to everybody? So it'll be just 2 and 4, not necessarily 3, but you may have to do stuff in chapter 4 that requires mathematics from chapter 3. It's best I can explain it. Okay. In fact, in a second here, you're going to see some of this vector mathematics stuff in action. Okay. All right. So let's just go ahead and plow ahead with these problems, example problems. I've got one more one-dimensional one for you. Well, it's kind of one-dimensional. It's from a relative motion point of view, it's one-dimensional, although it takes place in a vertical plane. So, but you'll see how it works. And then we'll get on to this two-dimensional stuff. Okay. All right. So any questions on business stuff before we head into the material? Okay. All right. So you got a helicopter, right, flying over a level field. And the speed of the helicopter is given there. And, it's this is taken out of a previous version of our textbook. And you can see this is one of the things you have to run into in this class and any other physics class is the authors don't always completely specify stuff. Okay, it's going at constant speed. Okay, we're doing a relative motion problem. So when you're doing relative motion, you have to say, okay, well, with respect to what? And I think you have to conclude that that speed is relative to the ground. Okay, and he said the helicopter's at a certain height above the ground. And then the helicopter's got a back door that points backwards, and you shove a package horizontally from the helicopter. And again, here's another thing that they don't quite tell you exactly what to do. Horizontally, what does that mean? In a direction opposite the helicopter's motion. Okay, so he saved himself there, right? Because it could have been like, okay, you're going forward and you could shove the thing out to the left, but you made it clear that you're shoving it out in the opposite direction to the motion of the helicopter, so that's backwards to the helicopter. Okay, and he correctly stated that the velocity is 12 meters per second relative to the helicopter. That's important. That's the important part. That velocity is relative to the helicopter. Okay, so find the initial speed of the package relative to the ground. What is the horizontal distance between the helicopter and the package at the instant the package strikes the ground? Okay, so this is kind of a combination of relative motion and also a little bit of projectile motion there, because what's going to happen to the package? It's shoved horizontally, and so this is going to be a problem very similar to what we did in projectile motion, where we fired an animal horizontally off a cliff, and the animal fell to the ground, you know, in a parabola. And you know, where does it land? How far is it from the base? So we're going to have to do a little bit of projectile motion and some relative motion. So how do you start this guy? Okay, so the first question, what's the initial speed with respect to relative to the ground? Okay, so you remember from last time, my go-to analogy in all of this is that walking back and forth inside a bus, right? It's your velocity relative to the bus plus the bus's velocity relative to the street is equal to your velocity relative to the street. So it's the same situation. It's always the same situation. It's just that it's instead of you, it's a package. Instead of a bus, it's a helicopter. Okay, but it's the same thing. Okay, so they give you the velocity relative to the helicopter. So that would be like your velocity relative to the bus, right? So it's your velocity relative to the bus plus the bus's velocity relative to the street gives you your velocity relative to the street. So it's the velocity of the package relative to the helicopter plus the velocity of the helicopter relative to the ground gives you the velocity of the package relative to the ground. Does that make sense to everybody? Go write it down here. Okay. VPRH, package relative to helicopter. VHRG, helicopter relative to ground, right? PRG, package relative to ground. Okay, writing this stuff down really helps, you know, in an equation. Okay, now these are all in one dimension, so we don't have to worry about vectors. Although I should mention this, because we're going to get into this in a second, that how do you go from one dimension to two dimension in these problems? You just take the same equation and you put vector hats over it, and you're there. Because the vectors, you know, in two dimensions will add vectorially. It's the only difference. It's either you go directly from scalar mathematics to vector mathematics without having to change the way the equation's set up. Hopefully that made sense. Okay, so package relative to helicopter, that's 12. Helicopter relative to ground, well, that was the 6.2, right? So if you plug all that in, remember the package is going backwards, right? So if the 6.2 is positive, the 12 has to be negative. Does that make sense, everybody? Okay. It's like walking backwards in the bus, right? Okay, so everybody, does that make sense to make people? Okay. Okay, good. And so there's your answer, 5.8 meters per second. All right. All right. No questions, we'll move on. What is the horizontal distance between the helicopter and the package at the instant the package strikes the ground? All right, how are you going to do that one? Okay, so the package is going to leave the helicopter and it's going to fall to the ground. Okay, while it falls, it's going to travel, and how far it travels will be determined by the velocity. Two things: by the velocity it's traveling at, the constant velocity it's traveling at, and the time it takes to fall to the ground. Right. So we're going to need the time it takes to fall to the ground. We've got the velocities relative to the ground right now. So first thing though is we need that time that it falls to the ground. So this is where we go back to the projectile motion stuff. And if you remember when we were firing things horizontally off a building or a cliff, it was just that vertical distance that determines the time it takes to fall to the ground. You remember that? And so I'm kind of skipping a few steps here that I would have done in projectile motion. You know, in the vertical direction, right? Ignore the horizontal direction for now. It's being fired in the horizontal direction, so there is no velocity in the vertical direction, no initial velocity in the vertical direction. If you start measuring the distance that it falls from where it starts falling from, the initial position would be 0, and then all that's left in the kinematic equation for the vertical direction, that's what that is. Like I said, I skipped a few steps here. This is basically, I'm starting with the kinematic equation in the vertical direction. Y of t equals 1/2 ayt squared plus v0yt plus y0. You remember that one? And then I've already simplified it down to everything we need, which is just 1/2 gt squared, where g, I've changed the a sub y to a g. Have you seen that? Have I done that before? Where I've changed the a sub y to a g? Okay, so I didn't fool anybody. That you will often see this in textbooks and problems. When it comes to the kinematic equation at or near the Earth's surface, they'll change a sub y, which is acceleration in the vertical direction, to g for gravity. So g means 9.8 meters per second squared. All right. And then solve for t, 2 times y over g. That's supposed to be the square root of 2 times y over g. Okay, and you stick the numbers in, and I get 1.4 seconds. So I skipped a lot of steps there. Does anybody need any further explanation of that? Did I skip too much here? I'm confusing everybody. Is everybody okay with what I did there? Because, well, let's see. Do I have, no, I've lost it. Okay, I don't have it. Okay, so remember, okay, y of t, let me write this down here, hold on. All right, there's the kinematic equation for y. And we're at the Earth's surface, right? So we're, at or near the Earth's surface. The only thing acting on the object, I mean, it did not say in the problem, but have we ever done a problem where there's air resistance in the problem? We haven't, and that's because it makes the mathematics insanely difficult. So we don't do that in projectile motion and in this course. You can, it's doable, but it takes some very sophisticated mathematics, way more than what we want to get into in this course. So for projectile motion, all these projectile motion problems, air resistance is neglected. So if air resistance is neglected and the only thing that's acting on it is a constant acceleration, the equations of motion are the kinematic equations. So in the vertical direction, okay, I said, okay, let's start measuring the vertical distance that it falls from where it starts falling from. So y0 is 0. It's propelled horizontally. So, that's 0, right? It's propelled horizontally. So y0 equals 0. v0y is 0, right? And so what's left over? 1/2 ayt squared. And I changed the a sub y to a g because that's what they do sometimes. All right. Does that make more sense now? Okay. Any questions coming in here? I see people typing here. What did I do? Yeah, you can either, at this point, yeah, I didn't put in the numbers for you, right? Okay, so everything's moving downwards. So it doesn't matter. It does not matter whether you call downwards positive or you call downwards negative. If you call downwards positive, then if you're measuring from where the helicopter is downwards, then y is going to be negative, right? And downwards is negative, so g is going to be negative, so the negatives cancel. Okay. If you call downwards positive, then the distance downwards is positive, and so is g. So either way you do it, you get a positive answer. Right? Remember, that's one of the things I tried to stress in projectile motion is that all you got to do is set up your coordinate system, and then you choose which direction is positive and which direction is negative. But once you choose which direction is positive and which direction is negative, everything that goes in the positive direction has to be given a positive number, and everything that goes in the negative direction has to have a negative number associated with it. So whether it's negative downwards or positive downwards, either one works, just as long as you stick to it. In this case, it doesn't matter. So you might as well call downwards positive. But you can call downwards negative, that's fine. The negatives will just cancel. Okay? We good? Moving on? All right. So we have the time it takes to go to the ground, right? So how do we go forwards from here? We want to know the horizontal distance between the package and the helicopter at the instant the package strikes the ground. Maybe a drawing might help here. Okay. Okay, so let's say this is the initial point where the package is fired from. And here's the ground. I missed my whiteboard. Okay. So the package gets fired backwards and then hits the ground there, right? And then the helicopter goes forwards, and I'm going to draw a little helicopter here. Okay, and there's the helicopter, right? And it goes forwards in a level horizontal direction, right? And at some point in time in the future, there's where the helicopter is, right? And we want to find that distance there. Does that make sense? That's what they're asking for. So, two ways you could think about doing it, right? Here's the point at which it was fired from, right? I could take that velocity we got from part A, which is the speed of the package relative to the ground, and I could multiply it by 1.4 seconds, and I'd have the distance between the drop-off point and where the package hits the ground, right? And then I could take the 6.2, which is the constant speed of the helicopter, and I can multiply that by the time, and that would be this distance here, and I could add them together and get the total distance. Does that kind of make sense? That's what I could do, but I'm not going to do it that way because there's a smarter way of doing it. Anybody think what the smarter way is? Remember, what's the 12 mean? Right. Does that make sense to everybody? I already got the velocity at which the package is moving away from the helicopter. Right? That's the velocity at which the two objects are separating away from each other. So I know what the speed is of that. So I just multiply that velocity by the time. That would be the entire distance. Yeah? So I just multiply the velocity of the package relative to the helicopter times the time. And that would be the total distance. And if you don't believe me, go ahead and do it the other way, and you'll see that you get the same answer. Okay. Any questions on that? Let that sink in for a little bit. This relative motion stuff, when you first do it, can be a little mind-bending. Okay? But you keep at it, and it starts to make a certain sense after a while. Okay. All right. I don't see any questions coming in, so let's go ahead and move on to the next one. This guy up here. Okay, so keep that on there in case you guys are taking notes or whatever. All right. So So this in rugby, I guess. I think this is also true in regular old American football. You can legally pass the ball as long as the pass is not considered, quote, forward, unquote, which means that I'm sure all rugby players are thinking this while they're playing rugby, right? It's just make sure that when you pass the ball, the velocity component parallel to the length of the field and directed towards the other team's goal must not be have a component that's positive. You think they're thinking about that as they play rugby? I don't know. Anyways, so if you're, let's say you're running forwards, right? So you've got a velocity and you're running forwards, and the ball also has that same velocity because you're holding the ball. If you throw the ball sideways, that ball is still going to have your forward velocity. Does that make sense? So now it's going to have two components of velocity. It's going to have a forward velocity and a velocity to the left or right. And if you add those two velocities together, you will get a velocity in the forward direction. So let me try and make a drawing of this, okay? So let's say you're running forwards, right, with your velocity, you're holding the ball, and then you throw the ball directly to the left. Well, so the ball is going to have a velocity component of that, and now you give it another velocity component of that, right? And velocity A plus velocity B gives you velocity C, right? This is how you add vectors together graphically. Okay, does that make sense to everybody? So this pass, if you did it this way, would be illegal. That's what they're saying. Because the ball has a forward component to it. Okay, any questions on that? Now we're doing this relative motion stuff. Which direction? Oh, you mean left or right? I don't. For this problem, I don't think it matters. Either left or right. But if that's what you're asking, I'm not sure what you're asking. If what the problem is asking is that what is the smallest angle from the forward direction that keeps the pass legal? So how do you keep the pass legal? Which direction do you have to throw the ball? Yeah, you have to throw it at least partially backwards. Partially backwards. You can throw it sideways, but it's also got to have a backwards component also. Does that kind of make sense? So in other words, well, I've got it drawn here, but well, let me just show you the drawing. Okay, it's already drawn nicely with a ruler, so that you can. So it's not so crappy, but so what you want is the end result to be the this guy here, right? Come back here, pencil. This guy here, you want that velocity to be at a minimum horizontal to the direction of motion. This is the direction of motion that way, and you want at a minimum for the velocity component of the ball to be sideways. Does that make sense? Okay. Right, so what you're essentially doing is, this is the velocity relative to the player, right? The ball relative to the player. And you're throwing it partially backwards so that the component of velocity of BRP that's in the direction that you're running forwards cancels your forwards velocity. Makes sense? Kind of, sort of. I don't like to say these relative motion things can be kind of mind-bending at first. But if you want to go back to first principles, if you're stuck, go back to the bus. It's your velocity relative to the bus plus the bus's velocity relative to the street equals your velocity relative to the street. Okay? So it's the ball's velocity relative to the player plus the player's velocity relative to the ground equals the ball's velocity relative to the ground. That make more sense? Because basically the ball's moving with respect to the player, right? It's like the ball is you in the bus is the player, and then you got the ground again. So you're measuring this. This is the direction he throws it with respect to himself, right? And then this is the velocity of him relative to the ground. And if he throws it away from himself at that velocity plus the player's relative to the ground, the forward component cancels out, and you want the ball's velocity relative to the ground to be in that direction. Am I making any sense here? This is really hard to explain. Okay. All right. That's the best I can do. Okay, it's the best I can do at this point. All right, so hopefully this makes sense. And you know what happens. So write that down, just like we did in the last problem, but with vector hats on it, right? So it's the ball's velocity relative to the player plus the player's velocity relative to the ground gives you the ball's velocity relative to the ground. Can you at least see the pattern involved here in, you know, something relative to something, something relative to the ground equals some, you know, that sort of thing, you know? So hopefully, you know, and it always works out this way. It always works out this way. Yeah. Okay. Yeah. Eventually, you know, you start getting an intuitive understanding of this stuff, but at first, sometimes it's just kind of like go according to just the scheme that I set up with you walking back and forth in the bus. All right. So now, what is the smallest angle from the forward direction that keeps the pass legal? Okay, so that dashed line there is the forward direction, okay? And so they want the entire angle from that. But the way this is set up, that's a right triangle, right? And that angle theta inside the right triangle, you're gonna have to take we're gonna have to solve for that guy, and then add 90 degrees. I think that's the easiest way of thinking about it. So which of those guys do we have? Okay, suppose a player runs parallel to the length of the field with a speed of 4. So that's going to be what? That's going to be the player's velocity relative to the ground. He passes the ball with a speed of 6 relative to himself. So that's going to be VBRP, ball relative to player. And what's the smallest angle then from the forward direction that keeps his pass legal? So they're not even asking what the velocity of the ball is. They want the angle involved. So how can I get that angle theta from what is it going to be inside the right triangle? It's going to be, we've got the opposite side and we got the hypotenuse, right? Yeah, right, exactly, sine. Does everybody see that? If that's a right triangle, then I know remember, these are vectors, right? And the way velocity vectors work is their lengths are equal to their magnitudes. Their lengths are their magnitudes. So if this is drawn to scale, then it would be, you know, the length of the opposite side divided by the length of the hypotenuse should give you the sine of the angle. Okay, so and I should have written down 4/6 because that's what the actual numbers are. But 4/6 reduces down to 2/3, right? Did that make sense? It should have been the VPRG divided by VBRP should be 4 meters per second divided by 6 meters per second. But that reduces down to 2/3. I got really lazy, okay? And so plug it into a calculator. Don't forget to change from radians back to degrees because we're in degrees. And add 90 degrees to the answer to get what they wanted. So 131.8. Okay, so angle. Did I really write that down? Wow, I'm so lazy. I can't even do proper grammar. Sometimes I wonder. Okay, any questions on that? All right. Right. All right, let's do some more of these guys. The more you see, the better. Track of the time here. Oh, we have plenty of time here. All right. Moving right along. Okay, everybody got that? All right. I'm going to take that over here, and then we're going to take this guy. And, all right, I'll show you this guy first. All right, so you can see this. Hold on. So another couple problems. So snow is falling vertically at a constant speed of 8 meters per second. Okay. And again, they didn't really say relative to what, so you have to kind of say it's got to be relative to the ground. Okay. They should really be more careful on this. At what angle from the vertical do snowflakes appear to be falling is viewed by a driver of a car traveling along a straight road with a speed of 50 kilometers per hour? Does that make sense what they're asking? Does it make sense that as viewed by a driver that the snow would be falling at an angle up according to him? The snow, if you're just standing on the road, the snow is falling vertically downwards, right? But if you're going horizontal to that direction, the snow would appear to be falling at an angle. That makes sense. Okay, no questions, so I'm assuming that makes sense. Okay, and then you take another look at the numbers and you say, oh, dang it, they're not the same units. And so got to do a unit conversion. Okay, so let's get that out of the way first. I gotta do a unit conversion. So I'm gonna go ahead and hold on. Just need to fill in. Yeah, at least they're both metric, right? So everything, well, except for the time, we're still stuck with 60 seconds in a minute and 60 minutes in an hour and 24 hours in a day. So we're still stuck with that. That's not like factors of 10. Otherwise, it would be easy. You come up with a metric clock. Oh well. Anyways, so 50 kilometers in 1 hour. This is the way. I don't know how do you guys know. You guys know how to do unit conversions, right? Any questions, right? So this is the way I always do unit conversions. I like to do them fraction-wise because that's kind of what you're doing. So 50 kilometers divided by 1 hour times 1 hour divided by 3,600 seconds, right? 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600. Okay, times, and that gets rid of the hours and changes it to seconds. And then there's 1,000 meters in a kilometer, and that gets rid of the kilometers and makes it meters. So in meters per second, the speed of the car is 13.9 meters per second. Okay, that's not too hard, is it? All right. All right, where do you go from here? Do I have a little drawing for you? I have a little drawing for you. Okay, and hopefully this will make sense here. Okay, so how do you look at it from a relative motion point of view? You've got the ground, right? And so there'll be a velocity of the snow relative to the ground, and there'll be a velocity of the driver relative to the ground, okay? So what other velocity is involved in the problem? And that's going to be the velocity of the snow relative to the driver, okay? Right, because that's, at what angle from the vertical do the snowflakes appear to be falling as viewed by the driver, right? So I need the angle of the snow, I need that velocity vector of the snow relative to the driver because that's the angle he's going to see relative to himself. I don't know if that makes a lot of sense. So going back to the bus, right? It's going to be the velocity of the snow relative to the driver. Yeah, I did. You caught me. I was going to go, mea culpa at the end of this problem. I should go back and change it. Okay, so just go with this for now. Yeah, well, you're right. You're right. Theta should have been in the other corner because that's the angle they're asking for. And I went and stupidly put it in the first corner because I wasn't thinking. Well, I just like charged. This is what happens when you charge into a physics problem without thinking. You end up like, oh, dang it. I would have been so much smarter if I'd done it the other way around. But, oh well, what's done is done. And I'm too lazy to go back and change it. And you get the right answer anyway. So back to the bus analogy. It's going to be the velocity of the snow relative to the driver plus the velocity of the driver relative to the ground equals the velocity of the snow relative to the ground. Right? U relative to the bus plus the bus relative to the ground gives you U relative to the ground. So the snow relative to the driver plus the driver relative to the ground gives you the snow relative to the ground. And they would have to go together in that way, right? According to that triangle, because it says that the velocity of the snow relative to the ground is vertical, downwards, right? And the velocity of the driver relative to the ground is horizontal. Okay, does that make sense? So I suppose you could, well, you need to see the angles involved. Here's how you write it down as a vector equation. Velocity of the snow relative to the driver plus the velocity of the driver relative to the ground gives you snow relative to the ground. Can you see how the velocity addition is always pretty much the same thing? It's right. It's the same thing as the bus. The only difference between this and one dimension is the vector hats. Yeah. Okay. All right. Well, I'm assuming you're gonna get that. Okay. So, which sides do I have? I've got the vertically falling snow, so I got VSRG, and I've got the velocity of the driver, VDRG. I'm missing VSRD, but I'm not interested in what that number is. I'm interested in the angle. So as drawn there, the wrong way, I should have put the theta in the other. I should have flipped this. I should have put the theta in on the other side of the triangle, because this is the angle they're asking for here. Okay, and I went and put theta down. And I do that because you're almost always measure angles from the horizontal. You get into a habit. All right. Any questions on this so far? I'm not confusing you. Okay. So do you understand that equation I just wrote down? VSRG divided by VDRG has got to be the tangent of the angle. Opposite over adjacent. Right? Okay. So if I do that, that angle there is 30 degrees, but of course that's not the angle they were asking for. So if that's 30 degrees, then the other one's got to be 60, right? 30, 60, 90 triangle. And I don't, have you ever seen that symbol before? I didn't draw it very well. Have I used that symbol? Did I use that symbol in a previous problem yet? You know which symbol I'm talking about, right? That guy. You ever seen that? No? Yes, no? Okay. You're going to see a few symbols in this course which are, I don't make these things up, okay? And you're going to think, no, that's just Larson. He's just making this up. It's not real. No, that symbol is supposed to mean which implies the following. So if theta is 30 degrees, then the other angle's got to be 60 degrees. Yeah, I know. And there's some other ones you're going to be like, really? That you just made that up. Yeah, but no, they really do. Like, there are some crazy symbols out there that we use in physics all the time. All right. So how about that one? Everybody okay with that one? Yeah? All right. All right, one more. And I think well, how much do I want to keep you guys up here? I think I used to tell myself I'm going to go 50 minutes for one of these periods because that's what we normally do, and then let you guys go off and do your, oh gosh, I'm behind. I need to put some more stuff up online, practice problems online. A little behind on that. I'll have that done today. All right, moving on to the next one. Any questions? All right, Next one. I'll show you the problem here. I don't want you to show the answer quite yet. All right, so here's a fancy one. You've got a department store. Remember those? Do anybody remember malls, like shopping malls? I think they're all dead now, right? Yeah, they're like, yeah. So they're having to convert them into Amazon packaging warehouses. Anyways, there used to be these things called shopping malls and department stores where people actually used to go to buy things in the old days. Back in your, yeah, it's right, like in the old days. And I'm old enough to remember this stuff. I'm actually old enough to remember a time before the internet, if you can believe that or not. I actually was alive before the internet was even a thing. It even existed. I know, and you're thinking, I know what you're thinking. It's like, what did you do for entertainment? You must have been so bored. How could you exist without the internet? It's just not, life is not possible. But, you know, somehow we struggled through. It's like, you know, old, you know, covered wagon days, you know, hitch up the old Bessie behind the wagon. Anyways, sorry, I'm rambling again. I do this from time to time. Senior moment. All right, so you got one, a daughter and a shopper, okay? I don't know why they call this shopper a shopper instead of a father, because the other person's their daughter, but I don't know. Anyways, you've got a shopper who's a father, and then the daughter who's the daughter of the shopper, and one's going up the up escalator and one's going down the down escalator. Do you guys know what an escalator is? Is that, it's still a thing? Okay. It's like this magical, yeah, it's like this magical moving staircase. Like where the stairs, the steps of the stairs move downwards or upwards, and you can just stand on the staircase and it magically elevates you up to the next floor or down to the previous floor. It's kind of like a, I don't know, it's a cross between an elevator and a standard static staircase. Anyways, hopefully you know what an escalator is. Yeah, it's so weird. I can't assume anything anymore in this class. So you can see the angles are the same from the horizontal down there in the drawing, right? The daughter's going downwards, the shopper's going upwards. Both speeds of the escalators are the same, okay? And so the question becomes, what's the velocity of the shopper relative to his daughter? In unit vector notation, no less. Oh my God, how are we going to do this? So I'm going to write this down first, okay? And then I'm going to draw the drawing, okay? So because this one's a little bit tricky, go back to the bus, okay? So I want to find the velocity of the shopper relative to the daughter, right? But then there's going to be some velocities relative to the ground. So the velocity of the shopper relative to the daughter. Okay, so that's like the shopper is you and the daughter is the bus. It's not very well. Okay, it's just an analogy. Don't take it personally. So the daughter is the bus. The shopper is you walking in the bus, right? And then you write the relation down the same way. So it's the velocity of the shopper relative to the daughter plus the velocity of the daughter relative to the ground gives you the velocity of the shopper relative to the ground. Does that make sense? Okay, all right. So how does that work? Okay, I'm going to show you the drawing here. And okay, so the shopper relative to the daughter. Okay, now how do I get that as being vertical? Well, think about the shopper relative to the ground. Okay. What's his velocity vector going to look like? Well, it's going to be a velocity vector that's 40 degrees up from the horizontal and moving at 0.75 meters per second. What's the daughter's velocity relative to the ground? Well, that's going to be a vector that's 40 degrees down from the vertical but also traveling at the same speed, 0.75 meters per second. Okay, so the length of VSRG and the length of VDRG has to have the same length because it's the same magnitude, same speed. Did that make sense? Okay, so you don't forget about the fact that that's vertical, right? Draw this guy and this guy first. They both have to have the same angle upwards and downwards for each one, and they have to have the same length. So if you complete the triangle according to the equation up there, that VSRD has got to be a vertical vector. Did that make sense? Okay, I know this is mind-bending stuff to begin with. Oops, to deal with this stuff, but hopefully that made some sense to you guys, right? If you just think about it just purely from just a vector point of view, that vector and that vector have got to have the same magnitude. One vector's got the same angle up as the other one has the same vector down, same direction down, angle down. What am I saying? Okay, I think I stumbled over my words quite a bit there. All right, no questions? Okay, we'll just move on then. So we need to find velocity of shopper relative to daughter in unit vector notation. How on earth do we do this? Okay, so basically what I'm going to do here is I'm not going to try and figure this guy out. What I'm going to do is I'm going to figure out what I can figure out. Can I figure out this guy, this V shopper relative to the ground? Can I figure that guy out in unit vector notation in a coordinate system fixed to the ground? Right? It's going to be we're going back to those components of a vector thing, right? A sub x is a cosine theta, a sub y is a sine theta, right? So VSRG would be the magnitude of the vector times the cosine of the angle, right? And that'd be the horizontal component, right? And then the vertical component would be a sine theta, so magnitude sine 40 degrees, right? And that would be the vertical component, the J component. Does that make sense? What I wrote down there so far? Okay, now how about the daughter relative to the ground? Can you do that one? We should be able to figure that one out as well, right? And a couple different ways of doing it. I use the negative angle, right? Does that make sense? That if you know that's the convention, right? Angles counterclockwise from the positive x direction are positive. Angles clockwise down from the positive x direction, or you can put them into your calculator as a negative angle. Right? Yes, right? Okay. Okay. No complaints so far, so I assume everybody understands. All right. So where do I go from here? Okay. I don't know if we've done this before, but take a look at that vector equation up there. And this, I don't know if this is obvious. It may not be obvious, but when you have a vector equation like that, right? Two vectors are added together to equal a third vector. You can just algebraically solve for what you want. In other words, what I want is VSRD, right? Well, I can just subtract VDRG from both sides, and that's something you can do vectorially as well as in a scalar form. So, as a vector, VSRD should be equal to vector VSRG minus vector VDRG. That makes sense. So you can remember you can add and subtract vectors, right? And you're just doing it vectorially. Okay, hopefully that makes sense. All right, so that's what I do. VSRD is equal to VSRG minus VDRG, just from that equation up at the top. And then just stick in what you've already figured out and subtract. So you can see that and this is just the same thing we did, with in IJK notation, right? When you add vectors, you add their x component. When you subtract vectors, you subtract their x components, and same thing for the y components. So I just subtract the x components and subtract the y components, and that's the new x and y components of the resultant vector. Any questions on that? Okay. And I don't know if this is obvious, but remember, if you think about it, this guy and both the daughter and the shopper, does it make sense, since they have the same angle and the same magnitude, that their x component of velocity should be the same? Okay, so as they both move sideways, if let's say that the shopper and the daughter start in a position so that the daughter is directly above the shopper, shouldn't the daughter always stay directly above the shopper? I mean, that's what this vector kind of tells you, right? Okay, so look what happens to the x component. It cancels. So from a relative motion point of view, they're both moving in the same velocity in the x direction. Stuff is hard to do. Okay, so anyways, there is the final answer. Okay, in IJK notation. There's just a j component, which, if you look at the drawing for the vectors, makes sense. He's just moving vertically upwards. All right. Okay, that, I think we're at 51 minutes, and that's as much as I'm going to torture you today. We got one more problem to do in relative motion, one more example problem, and then hopefully by next time I'll have a date for you for that little assessment we're going to do. In the meantime, look for more practice problems to show up on Canvas in a couple, 3 hours maybe after school. And then if you haven't done the feed the monkey thing, get that done. What else is out there? You could be, hopefully you know enough now you can start working on the rest of the chapter 4 homework problems. All right, anything else? Any other questions about what we're doing or where we're going, or any things with the questions or the example problems we just did? Because if there isn't, then we will see you on Thursday. Okay. Okay, we'll see you guys. Take care of yourself. Have a great rest of the day.